Thank you very much. François has used that the titles of my talks usually contain quadrant orbits, but this time the quadrant orbits do not appear in the title, but they appear in the talk. Can you hear me if I speak without? Because I wouldn't like to be recorded. So I think that if you can hear me, I will try to speak like this. Can I use it? Okay. So we are interested in in incompressible fluid. So I recall this Arnold setting that the Euler's equation for an incompressible fluid can be seen as a geodesic equation on the group of volume-preserving diffeomorphisms. So here M is a manifold of, one can do it in any dimension, and endowed with the Riemannian metric. I will restrict this in this talk to M equal R2, to the plane. But let's see the vorticity for an ideal fluid. So the vorticity lives in the dual of the Lie algebra. So you have the Lie algebra of divergence vector fields. And the smooth dual, the regular one, can be seen as one forms modulo exact one forms. But in the special case when H1 of M is 0, this here we recognize the vorticity 2 form. And the vorticities, they so in the 2D case, we are we have the group of volume-preserving diffeomorphism of the plane, but in the plane the volume form is also a symplectic form, and so volume-preserving diffeomorphisms will be Hamiltonian diffeomorphisms, and we take compactly supported so that we have a nice Lie group structure, and then the Lie algebra can be identified with Hamiltonian vector fields, and we choose the Hamiltonian function with compact support. Hence, the maybe I would show it here first. Hence, the space of vorticities are just dual of the Lie algebra. So the densities on R2. So on one hand, one has the regular ones that you saw. There are these two forms, but I'm interested in the singular ones. So in distributions, they will have nice support and controlled singularities. I listed here a few of them which I'm interested in. I listed them here with the pictures. So the first is the well-known point vortices in the plane. So this is the codimension 2 case. It behaves in an analogous way with in R3 we have the vortex filaments. Then we have the codimension 1 case. So then we have a loop, a vortex loop in the plane. So this is the analog in 3D would be vortex surfaces. They are called vortex sheets, and they come foliated into vortex filaments. So the vortex sheet is endowed with the vorticity density, which is closed one form on the surface. In the case of in the 2D case, we have this vortex loop together with the vorticity density on the loop. So one can see it as point vortices aligned on a curve. So one can consider dipoles also as singular distribution or a loop with attached dipoles. But before of this, one can consider loop points attached on the loop. And one can consider also a full loop of dipoles. So here, this is joint work with my student Ioana Ciucla. This is joint work with the dipoles with Francois and with Jerry Goldin. And this is joint work with Stefan Haller. So here we have a dual pair that it is appears in the description, and I will talk about this here. Here also we have a dual pair. The picture that I skipped here is from a paper of Isosimov and Casey. When they describe the regular coadjoint orbits, one can describe them using red graphs. So what I'm doing, what I want to talk about today, I will present point vortices and then the vortex loops, and then an attempt to discretize this vortex loop and to see how related it is so with the family, not a continuous family of points on the curve, but a discrete, like a polygon to approximate the curve with the polygon. So first about the vortex points. So this is a classical, so we have k points in the plane. Oops, this is the diagonal, but we are k here. We have here should be k, not n. K points in the plane who are distinct. So from we remove this fat diagonal when at least 2 points coincide. So this configuration space of k ordered points in the plane can be endowed with a symplectic form. Here we just pull back the symplectic form on the plane, and we have these vorticities or circulations for each point vortex. And in this way, the configuration space with this symplectic form becomes a coadjoint orbit for our group of area preserving diffeomorphisms. But this is in the case when all the vorticities are distinct. If some of the vorticities coincide, for instance, if all the vorticities coincide, then the coadjoint orbit is the configuration space of unordered points. But we can have also a space in between, a case in between, when we partition the vorticities into those that are equal, and then we take the permutation subgroup, preserving, this is sigma gamma, preserving this partition, and we factorize the configuration space by this, and then we get again coadjoint orbits of our group of area preserving diffeomorphism. This was the point vortex, the first case, and now it's the case of vortex loops. So the codimension 1 case. As I said, we endow the loop, the curve C, with a vorticity distribution. So we take the case when it is nowhere zero, so it is a volume form on the curve. We denote by W the total volume, the total vorticity on the curve. So it is an element, I'm sorry, it is an element in the dual, so it's a density, a distribution in this way. We just integrate the function over the curve with this one form. And there is a natural action of the group of volume preserving area preserving diffeomorphism just by pushing the curve and the density. Since what are the invariants? We have the enclosed area because it is area preserving, and also the total vorticity is preserved by this action. And indeed, the orbit is given by these are the only invariant, the total set of invariants. One can view this. This will be a quadron orbit. One can view it also as here is an unparametrized curve. We can see it as parametrized curves modulo the action just by rigid rotations. This can be seen in this picture because if we are given the curve and at beta, the one form, then we can just start somewhere with the parametrization, let's say at x0. So f of 0 will be x0, and all the other, then the parametrization is so then the parameter of the is given by beta. The parameter of x is just 1 of the W integral from x0 to x of beta. It's just like the how do you say it, the arc-length parametrizations were up to a rigid rotation. So so indeed we have this identification, and let me say also that in each of these orbits we have a unique circle that is the true circle centered at 0 and uniformly distributed vorticity. So this will these are kind of saying parameters for the space of orbits of this type. And please tell me how much time do I still have? 7 minutes. This is the dual pair due to Marsden and Weinstein, so ideal fluid dual pair. It appeared in the very nice paper from '83. So with Francois we worked on it, and we showed really it is a dual pair. So maybe it's easier to understand it in terms of these mutually completely orthogonal actions. So the expression, this term was we found in the paper, in the book of Lieberman and Marl. So it's about on the space of embeddings, we have the left and right action. For from the left, we act by Hamiltonian group. From the right, by the group of volume preserving diffeomorphisms, and they preserve this symplectic form, which we saw also in the talk of Professor Spera. And these actions are mutually completely orthogonal, so this means that the orbits are symplectically orthogonal to each other. But I'm interested in this dual pair for in our 2D setting. So what we have here is parametrized curves. The symplectic form is the simple one. We have two vector fields along the curve. They're inserted into the area form and integrated over the circle. And the actions from the left and the right are these groups, and they have momentum maps. And the momentum map here is just the enclosed area, and the momentum map on the left is just the distribution by pushing forward. So it's a nice simple dual pair, and there is this general principle that if we do reduction on one leg of the dual pair, then we get coadjoint or automatically coadjoint orbits of the group for the left action. So in our case, it's just a group that we are interested in, the group, the area preserving group. And indeed, by this symplectic reduction, so when we take A here, we do symplectic reduction, we get our coadjoint orbits. And this coadjoint orbit, so we can see also the decomposition into this QP decomposition of W type. But for this we have to use an ambient metric, the Euclidean metric on R2. So this is how the curve itself is the support, how it is deforming, and this tells us how to deform the vorticity density, the one for beta on the curve. And then the KK symplectic form, which descends from this big omega that we saw before, because we have done symplectic reduction, then it's really using the non-degenerate pairing between zero integral functions and exact one forms. So one understands very well how the KKS form looks like. And I think I will not enter into these details. We also studied the prequantization with Francois, and we showed that the prequantization condition is that the product between this enclosed area A and W, which is a total vorticity, has to be an integer. And we also showed that really this condition is necessary and sufficient. We called it the Onsager-Feynman condition. This is how Jerry Goldin and collaborators used it in they studied the 3D case, but with some ribbons of vorticity, some vortex sheets that are infinite, without boundary, non-closed ones. But I will not enter into these details because I want to go to, but maybe I can show this because it has a picture. We also computed the character, and it is given, but it's also, they have, we can find in the Goldin Mednikov-Sharp paper too. It includes it uses this area. So we have phi, the area preserving diffeomorphism, so this is our curve, and then we integrate, so we take a path from infinity to x, and this is the image by phi of this path, and together with so if the curve is oriented, so together with this curve segment from x to phi of x, we have delimited an area, and this will be integrated over the curve using the vorticity density. But what happens if phi of x comes from the other side, it's near x? Then what do we have? We go from infinity to x, then we follow the curve in the orientation, and then we go back with the path, with the image by, with the path moved by phi. So this will not give us 0, but this will give us the enclosed area. And you see, if we integrate here the enclosed area, which is constant, and then we get this the total vorticity, which is W, so we get A times W, and this again explains the Onsager-Feynman prequantization condition. So this was about vortex loops. And now, what would be a discrete version? And I hope I have 2 minutes. Okay. First, as I said, we take f is a parameterization of the curve, and we fix k points. We get xi is the point with parameter ti, so we get an element in the configuration space. So in this way, we get a polygon. We will allow also polygons with self-intersections for convenience. What is the analog of the vorticity density? So we will here also have discrete versions. So we have a collection Wi of partial vorticities. This is the vorticity between these halfway points between xi and xi plus 1 and so on. So we just integrate beta on the curve segment between these points. So we get a partition of W into partial vorticities, and then the symplectic form, the version, the discrete version, is very similar to the one that we got for point vortices. We had there gamma I, the big gamma, which was the circulation, but now it is replaced by this Wi, these partial vorticities. And now we had the rotation action on embeddings, the action from the right, but now we don't have such an action on the space of polygons. But still it survives on the infinitesimal level. So it survives through this vector field on the configuration space, so on the space of polygons. I have a picture here. So this is the polygon that approximates the curve, and at each point, this is parallel to this segment, and it is scaled, as you see here, by the partial vorticity. So this is xa plus 1 minus xa minus 1. So we have also a kind of rotation action, but only on the infinitesimal level. And now we want to mimic the symplectic reduction. But first, we noticed that we have also the analog of the enclosed area, which is the polygon area. So omega here is the area form. And with the symplectic form sigma I showed you before, zeta is exactly the Hamiltonian vector field with this function as a Hamiltonian function. So in particular, these dynamics given by zeta, so it preserves the enclosed area, the polygon area. And this is my last slide. Now we can mimic the we get a discrete version of the quadrant orbit of vortex loops, but only on the infinitesimal version, infinitesimal level. So we get a symplectic vector bundle. So we have the kernel of the differential of the area function, and we mod out the rotation action, but we only have it infinitesimally. Zeta is this vector field. So it's a vector bundle of rank 2k minus 2. No, 2k was the configuration space, minus, so you have 2 dimensions lowers, and it's over the submanifold with the polygons of enclosed area, constant enclosed area in the configuration space of all polygons, not necessarily simple. And now this is kind of an, I couldn't answer this question. If the flow of zeta is nice, then we can factorize by the trajectories of the flow, and then we could make sense of a quotient manifold, so to integrate this and to to get really not only an infinitesimal description on the discrete level, but this, I don't know, maybe it would be nice to understand better the dynamics of this vector field zeta on the space of not necessarily simple polygons. Thank you very much.
Thank you very much. Are there some questions? Yeah.
So there is rather comment. As far as the Feynman-Zeiger condition is concerned, which is the integrality of the conjoint orbits, that it is also mentioned in an old paper by Vittorio Penna and for the loops, at least in the three-dimensional case. Yeah, yes, indeed. Because it's also this in this paper of this work of Briniski, which I mentioned that there is a construction, a more general construction of the pre-quantum line bundle via Gerbs. This is quite.
We also have a construction of the pre-quantum line bundle. But is this the codimension one or two case in this paper dimension? The curves in R3 of surfaces in R3.
This with vortex loops.
Loops in R3, because then the pre-quantization condition is a very different flavor. There one just needs the integrality of the volume form and if it's in a closed line form. Yes. So it behaves differently in the codimension 2 case from the codimension 1 case.
Also, I think that in the point vortices you have in general representing the abelian representation of the break group, because when the vortices coincide with this, you can construct also some example of Laflin wave functions from this, because they are representations.
This would be nice if you could explain us, because the next step that we want to take is to see if we get meaningful representations associated with these conjoint orbits, and this is work in progress.
Thank you very much for your most interesting.
Other questions? If not, thank you again.